Good morning everyone, I am Mr. Ish. We're looking here at a video on even and odd functions and their presence in differential calculus and integral calculus. If something is even by means of the test, we know from precalculus even functions f of x is equal to f of minus x. These are always equal. If you had cosine of pi over 6, it would equal to cosine of minus pi over 6. Easy, right? Likewise, if you had square x square, it would also equal to same as minus x whole square. F of x is equal to f of minus x. These are functions which are symmetric about the y-axis. And then there are odd functions. These odd functions have origin symmetry. They're symmetric about the origin. Example of a good test for an odd function is if you had f of minus x, the function would become minus f of x. This right here is a test for an odd function. You could see sine of, let's say, minus pi over 2 would be the same thing as saying minus sine of pi over 2. You can look at x cubed. If you had, like, let's just say minus x and then you cube it, it should equal to minus an x cube. It would be all the same with regards to odd functions. So this right here is a good test for an even function with y-axis symmetry. This here is a good test for an odd function with origin symmetry. In this video, we're going to be looking at some of the important or interesting trends that develop with regards to even and odd functions with regards to derivatives and integrals. A very interesting trend with regards to derivatives is this. When you have an even function you take as a derivative, you will generally, most of the time, develop an odd function. Let's look at this first part here, even function derivative giving rise to odd function. Think about it. Derivative of cosine x gives you sine x. It's an odd function, and this right here is odd even with the presence of that negative, and you know why. If from a very limited domain, let's just say from pi over 2, minus pi over 2 to pi over 2, sine looks something like this, the minus sine x would look something like this. It would just be a reflection of it, but it would still be an odd function. Derivative of x squared, a very famous even function, gives you 2x. This here is an odd function. It's a linear line with origin symmetry. It will have a steep slope, and this right here is an odd function because if you did 2 of minus x, it would be the same thing as minus 2x. F of minus x is equal to minus f of x. How about this one? Derivative of this radical function 1 minus x squared. You know this right here is an even function because it would look something like this, from minus 1 comma 0 to 1 comma 0 going up to 0 comma 1. It's even. Y-axis symmetry is an even function. When you do the derivative of this, you have to use the chain rule. You would get minus x over square root of 1 minus x squared. If you were to graph it, you would get something like this. With regards to these asymptotes you have over here, you would have something which would look like this, and that right there will have origin symmetry. It would be an odd function. You could even say that it is an odd function by using the test. Wherever you have x's, you know for the odd function you have f of minus x is equal to minus f of x. Wherever you have these x values, just put a minus x. You'll have a minus x. Here you'll have 1 minus x squared. You can operate on this and you'll get, what will you get? You'll get x over square root of 1 minus x squared. This right here is no different than just hitting everything with a minus 1, multiplying it, and you'll get exactly that. F of minus x is equal to minus f of x. So very generally, and usually most of the times, even function derivatives give rise to odd functions. Let's look at the reverse case. Odd function derivatives give rise to even functions. Derivative of sine x will give you cosine x, and you know that's a even function. We're looking again from minus pi over 2 to pi over 2 to as high as 0 comma 1. We have this even function developed for a cosine, and you know it's going to extend in this direction. It will have y-axis symmetry, and in all parts from a minus a to a positive a interval, it will always be an even function. Derivative of a cubic function will give rise to 3x squared. You know, an odd function giving rise to an even function, it will have a vertical stretch, but it will still be a parabola with left side and right side symmetry. It's symmetric about the y-axis, and it is indeed an even function coming off from a derivative of an odd function. Derivative tan x, an odd function, gives rise to secant square x, and this right here is indeed a even function. Ignoring the asymptotes, you would have graphs which would look something like this. generally, but they'll all be even. Y-axis symmetry. Derivative of x, a linear line having origin axis symmetry, you will get 1. 1 right here is indeed an even function, because if you graph it, you're looking at y equals 1. Y equals 1 from any domain. If you do a domain like from minus a to a, and you limit this one line, y equals 1 line, you'll always have this part right here equal to this part right here, having y-axis symmetry, and indeed it is an even function. So keep in mind, generally speaking, even function derivatives are odd results, and odd function derivatives are even results. In integral calculus, we know that anytime you're looking from an interval minus a to a for a function and you do its derivative, you can modify the interval such that you can look at from 0 to a f of x dx. It would be exact same result. The reason being, if you look over here at this, and we'll come back to a parabola because you can do this equally well with the cosine function, but we'll stick here with the parabola from minus a to a. If you look at this portion here in the area below the curve with regards to this x-axis and the area below the parabola, this area will always be equal to this area, and you could essentially double everything from 0 to a and times it by 2. You could also look at this coordinate as minus a comma 0 and this coordinate as a comma 0, and if you were to look at this segment over here, and you can do the distance formula, you can do y2 minus y1 whole square plus x2 minus x1 whole square, and you'll get within here a 2a whole square, and you'll get square root of 4a square. When you do this perfect square and you square root it, you'll get a 2a, which means you're basically looking at a segment that's 2a, and you can very well bring this 2 and bring it right out here, and you can very well establish from a 0 to a the interval, because from 0 to a is just a single a, you double it, you get your double a, which is 2a, and you see that reflecting there in the modified interval. If you have an even function, you can also show that minus a to a for an f of x dx should also equal to minus a to a f of minus x dx. For an even function, f of x is equal to f of minus x. From here, if you look at this part specifically and you use polynomial substitution, u is equal to minus x, du is equal to minus dx, dx is equal to minus du, and you modify your intervals according to this, because they do modify. You have definite intervals here. u1 is equal to minus a, it becomes a. u2 is equal to minus of that positive upper limit, and you get a minus a. And this interval becomes from an a to a minus a, f of u and du, but you have a minus du, so you can bring a minus. The fact that we have a minus over here, then we have a larger number here as a lower limit and the smaller number here as the upper limit, you can use the properties of intervals and negate everything with a minus and flip the intervals back, and you'll have f of u du. When you do this procedure here, the minuses can disappear, because minus times minus is a positive. You end up with minus a, and then f of u du, and you can show that this right here is equal to this expression right here when you do the definite integration procedure, because if you do the definite integration here, you'll do f of a minus f of minus a. Remember the upper limit and the lower limit with regards to your antiderivative, and we can demonstrate the antiderivative here with a capital F. There's nothing wrong with using a capital F. When you do your definite integration here, you'll here end up doing f of a minus f of minus a, and you'll have your definite numerical result here and definite numerical result here, and they should be the same because they are exactly the same. And that's the beauty of an even function. F of x is equal to f of minus x, and in all of this regard right here, you could have even just put a 2 outside and a 0 to a, and you'd still get the same result. But I'm just keeping everything here from minus a to a just for this part. So you can see for an even function, minus a to a is equivalent to 2 multiplied by 0 to a, and f of x for that definite interval is equal to the integration of that, similar to that of f of minus x with the same interval. It all equals to one another, because this is a definition of an even function. F of x is equal to f of minus x. Now in the last part of this video, we just talk about odd functions. with regards to integrals. You know, for an odd function, you have f of minus x as a test is equal to minus f of x. When you're doing a definite integration procedure from minus a to a for an odd function, you know the net effect is always 0. We've talked about that as one of the integral properties. You can take any odd function from minus a to positive a. We take a cubic function. You have a net effect here, minus area over here, and you have a positive area over here, and the net value here is always 0. What we can do in the next few minutes is show you why this is the case and derive and prove why the net effect for an odd function from a minus a to a positive a interval is always equal to 0, and that would be a useful exercise to do. So to show why for an interval from minus a to a, an odd function always has a net effect of a 0 in terms of the net area, we have to establish integrals in this form that you see over here. F of minus x equals minus f of x. We use the test for an odd function to do that. You'll have from interval minus a to a, f of minus x dx is equal to minus, then minus a to a, f of x dx. Here you have a composite, so you do polynomial substitution technique. U is equal to minus x, du is equal to minus dx, dx is equal to minus du, u1, everything with regards to this and these coming in places of x, you have u1 is equal to a, u2 is equal to minus a. We put those values here. You'll have a here, minus a here, you have a minus sitting outside, f of u du. This minus is exactly this minus right here. It will equal everything you see over here, minus. From minus a, f of x dx. In this next step, you have to do nothing more than just your definite integral procedure, this side and this side, and make them equal to each other. Here you have a minus. We can represent this as our antiderivative for the f functions. You'll have f of minus a minus f of a is equal to, here you have a minus sitting here, you'll have an antiderivative with regards to this a minus that with regards to the minus a. Open up the parentheses. When you open up the parentheses, it impacts everything you have over here. You'll have a minus f of minus a plus f of this a is equal to minus f of this a plus f of minus a. Bring all the like terms, which are these two, and the other like terms on the same sides of the equal sign. Here you'll have a minus 2f of minus a. See, this comes on this side and you get a minus 2f. Take this on the other side and you get a minus 2f of a. The minus 2's can cancel out because they're equal on both sides. You can just cancel them right out. What you end up having is f of minus a is equal to f of a. You can take this onto the other side and you'll have nothing left over here, which is represented by 0. You'll have 0 is equal to f of a minus f of minus a, and here it is, showing you why the net effect for an interval from minus a to a for an odd function is always equal to 0. If you didn't go through this procedure and you wanted to establish an integral that would give you this, it would be exactly this, minus a to a f of x dx. An odd function, upper limit a, lower limit minus a. If you do the derivation in terms of the definite integration, you get exactly this. So we've proven and shown you why the net effect for an odd function is always 0. And in this video, we've also shown you why for an even function, a minus a to a is similar to as saying 2, but from 0 to a. We've also shown you why here in this video the derivatives, even functions give rise to odd functions generally, and odd function derivatives give rise to even functions. And you've seen that at the beginning of this video. That's all I wanted to show you in this video. Thank you for watching and have a nice day.